Welcome everyone to this week's science news. Today we'll talk about mysterious radiation bursts, a superfluid that supposedly recreates the early universe, good news from the Webb Telescope, plans to intercept the next interstellar object, why you shouldn't make things more complicated than necessary, a new device against tick bites, and the good and bad of social media. Scientists believe that several radiation bursts struck Earth in the past 10,000 years, but they still have no idea why. Tree rings carry traces of carbon-14, that's a radioactive isotope of carbon, which is normally present in the air at a steady amount. But a few times in the past, the carbon-14 level seems to have sharply risen. This was originally discovered in 2012 in tree rings from Japan, dating back to the 8th century. The events are now called Miyake events, after the lead author of the first paper. The same was later seen in tree rings from several other countries, including Germany, Russia and the United States. And not only this, scientists have since found evidence for several more such events in tree rings. By now they count 6 carbon-14 spikes, the earliest about 9,300 years ago. However, it's remained unclear what caused the carbon-14 level to rise. The most widely accepted explanation is big solar flares. That's because carbon-14 is created by protons which hit nitrogen-14 in the upper atmosphere. The more highly energetic protons come from the sun, the more carbon-14 they produce. So a big solar flare could cause a peak in carbon-14. Those solar flares would have to be bigger than even the 1859 Carrington event, which is the biggest solar flare on record. That's quite scary. I talked about the Carrington event in an earlier video. However, there are a few problems with the solar flare idea. One is that ice cores, which preserve samples of ancient air, show no traces of radiation spikes that coincide with those of the tree rings. Another problem is that the same traces were not found in trees near the poles. A new study that was just published in the Proceedings of the Royal Society adds more evidence against the hypothesis that the Miyake events were caused by solar flares. According to the paper, the events do not align with the solar maxima, which occur every 11 years and which make solar flares more frequently. This in and by itself doesn't rule out the solar flare idea, but it disfavors it. They also say that 2 of the events seem to have lasted more than a year, whereas solar flares only last a few days. This also speaks against other astrophysical explanations, such as nearby gamma-ray bursts or supernovae. One of the authors of the paper, Benjamin Pope of the University of Queensland, says that there's about a 1% chance of such an event occurring in the next decade. He isn't particularly worried about it. In his own words, "I'd be more worried about being hit by a bus on my walk to the office." I think he isn't taking this seriously enough. When a radiation burst knocks out everyone's phone, what are we supposed to do? Talk to each other? A paper that was just published in Nature claims to have used a superfluid to simulate conditions similar to those in the early universe. It's an experimental work from a group of researchers in Germany. They used a cloud of about 23,000 potassium-39 atoms, which they cooled down to a few nanokelvins. At this temperature, the potassium cloud becomes superfluid, which means that its viscosity drops to 0. The cloud of superfluid atoms is held in place by magnetic fields. That allows the researchers to change the shape and density of the cloud, which in return allows them to control the speed of sound in the fluid. This doesn't mean the superfluid plays music. The speed of sound is just the speed at which density perturbations travel. What's all this got to do with the early universe? Not very much. If you poke such a superfluid and create density perturbations in it, then the perturbations have quantum properties. It's been shown mathematically that perturbations in a suitably prepared superfluid spread similar to how perturbations would have spread in a rapidly expanding early universe. The measurements in the new paper confirm these expectations. This research area is known as analog gravity because the superfluid is supposed to be an analogy to gravity. Mathematically, that's correct, but one doesn't learn anything about gravity from it that one didn't know already. In the best case, this experiment can be said to test textbook calculations for the early universe. No one doubts that the calculations are correct. The question is whether the equations are the right ones for the early universe. Superfluids in the laboratory can't answer that question. The magazine Nature loves publishing experimental physics papers, but basically never publishes theoretical physics papers. One of the consequences is that the theoretical motivation for the experimental studies remains largely unchallenged. Albert is somewhat confused about the difference between superfluid and superfluous. The Webb Telescope is fully operational again after engineers found a workaround for a technical problem. The mid-infrared instrument, MIRI for short, on board the Webb Telescope has not been used since August 24th. The mid-infrared instrument is one of the most important instruments on board the Webb Telescope. It covers the wavelength range from 5 to 27 micrometers and can be adjusted to cover the longer, shorter or intermediate wavelength range. According to a report from NASA in September, one of the wheels of the mechanism to adjust the wavelength window of MIRI wasn't working properly and seemed to be experiencing increased friction. A new report, which just appeared last week, says that they have since made numerous measurements to understand the unexpected behavior of the wheel and have come up with an updated plan to account for the increased friction. They are now preparing to return the instrument to full science operations. The Webb Telescope has been collecting data with its other instruments since July. It has a broad mission that ranges from studying early stars and galaxies to the large-scale structure of the universe, the formation of solar systems, exoplanets, and our own solar system. A team of American researchers, including Avi Loeb from Harvard University, have put forward a proposal for how to deal with the next interstellar object in our solar system. Astrophysicists made their first observation of such an interstellar visitor in 2017. The object, named Oumuamua, had a rather unusual shape similar to that of a cigar. It came from outside our solar system, approached the Sun, then accelerated and left. At the time, it was unclear what to make of this observation, but a few years later, most astrophysicists concluded it was a natural object, most likely a big chunk of frozen nitrogen that broke off from a bigger object. When it approached the Sun, the frozen nitrogen began to evaporate, which accelerated the object and propelled it back out of the solar system. The Harvard astronomer Avi Loeb has claimed that Oumuamua was the first sign for intelligent life beyond Earth. When he noticed that the headlines made him very unpopular with his colleagues, he tried to backpedal, an exercise that turned out to be difficult, seeing that this claim is the subtitle of his book. Be that as it may, astrophysicists agree that next time an interstellar object comes to visit, it'd be good to get a closer look before it disappears, because you never know, maybe there are little green men on it. In the new paper, they say that the most likely way to discover a new interstellar object will be with the Vera Rubin Observatory that is expected to start collecting data soon. We just talked the other week about the completion of its camera that is soon to be shipped to China. According to the new paper, we can expect to see about 15 interstellar objects with the Vera Rubin Observatory in the next 10 years. That's between 1 and 84 with 95% confidence. Or, to put it differently, they estimate that the chance we'll not see any interstellar objects in the next 10 years is about 1 in 20. They suggest some instruments that such a probe to an interstellar object should carry, but most importantly, they say it'd take too long to launch the thing from Earth, and it'd be better to park a well-equipped spacecraft out in space, maybe in the same region as the Webb Telescope. Making a model more complicated to fit more data points is a bad practice known as overfitting. So far, so clear. But what should scientists do if they have to decide what data their model should fit in the first place? Is it always better to make a model more general so that it applies to more cases? Or should you focus on that which you're pretty confident you understand? The usual statistical measures to avoid overfitting don't work in this case. A new paper that just appeared in the journal Science Advances proposes a new way to evaluate models by using what they call the effective dimension of a model. This effective dimension is a measure for the number of parameters that strongly depend on each other. Loosely speaking, it's a way to quantify the complexity of the model. The authors show that increasing the complexity of the model tends to also increase the uncertainty of the model outputs, because those parameters all influence each other, and that complex models can convey a false sense of accuracy. Moreover, if you have a model that produces more predictions than you have good data, then you can't properly assess how good it is in the first place. They discuss several examples of models which have this problem. That includes pandemic models and climate models. Based on their analysis, they propose that scientists evaluate the effective dimension in each step of the model development. They stress that their point is not that simple models are necessarily better, but that a model should be adequate to the situation and to the available data. In their own words, such a control is especially needed to prevent policy-oriented models from getting as complex as to cloak value-laden assumption and output uncertainties. Or, as the great scientist Avril Lavigne put it, why do you have to go and make things so complicated? I think the authors have put their finger on a sore spot in model development in many disciplines, and that this paper will become very influential. Hello? Mr. President? Carbon offsetting? Yes? No, we don't sell equations, sorry. But I can put you through to the economics department, 1 second. Scientists have tested a new device to prevent tick bites. As the climate changes, insects and other parasites like ticks change their habitat and spread diseases. Ticks in particular can infect humans with nasty illnesses such as Lyme disease, Rocky Mountain spotted fever, and several other conditions I don't know how to pronounce, but that I'm sure are very unpleasant. So far, protection against ticks has focused on contact repellents. That's the stuff that you spray onto your skin and that deters insects when they come in contact with it. The new study from researchers in Maryland and Massachusetts focuses instead on a method called a spatial repellent. They use a controlled release device for the chemicals that inhibit the parasites. This isn't a new idea, but it's the first study to systematically look at what this stuff does to ticks. They put the release device and the ticks into a cage with poles. Then they tracked how well the ticks could crawl up the poles with a video camera. According to the authors, the chemicals put ticks in a drunken-like state that makes it difficult for them to climb. The results may be useful to determine under which circumstances using spatial repellents is effective. According to a new study published in Nature Human Behavior, social media is both good and bad for democracy. A team of international researchers analyzed 496 different studies examining the link between digital media and democracy. Here's how citing 496 papers in one sentence looks like in HTML. First, the good news. The researchers found that the global adoption of digital media allowed higher rates of political participation and increased the consumption of information. Both of them promote democracy, especially in autocracies and new democracies. Now the bad news. Increased adoption of digital media is associated with a decline of political trust, the growth of populism, and an increase of political polarization, all of which have negative effects on democracy. So basically, social media is good because we use it, and bad because they also use it. The researchers also found that exposure to misinformation occurs more often in established democracies. According to another paper that was just published 2 weeks ago, people from the UK, Canada, Australia and New Zealand are exposed to misinformation on social media at about the same rate, but Americans are 3 times more likely to share it. According to an analysis from the campaign group Global Witness, the number of delegates with links to fossil fuels at COP27 has jumped up by 25% from the last meeting. Security at location expressed serious concerns for the health and safety of fossil fuel lobbyists as they appear to be chronically stuck in the past. When I started those science news, I wasn't really sure it's for me, but it turns out I like working on it because I constantly learn new things. If you also like learning new things, but in a more structured way than just watching YouTube videos, our sponsor Brilliant can help you with that. Who or what is Brilliant? Brilliant offers courses on a large variety of topics in science and mathematics. It's an amazing tool for learning. There's so much to find there, and they are expanding their content each month. All their courses come with interactive visualizations and will challenge you with questions, so you can check your understanding right away. I have found Brilliant to be really effective to understand something and also to get it to stay in my brain. I even have my own course on Brilliant, which accompanies my videos on quantum mechanics. This course will introduce you to quantum mechanics starting from the very basics, so you don't need to be an expert already to understand it. My course gives you an introduction to interference, superpositions and entanglement, the uncertainty principle and Bell's theorem. If you're interested in trying Brilliant out, use our link brilliant.org/Sabine and sign up for a free trial where you'll get to try out everything Brilliant has to offer for a whole week. The first 200 subscribers using this link will also get 20% off the annual premium subscription. Thanks for watching. See you next week.